leave screen and the live streaming in YouTube. Now it's setting up.
Okay.
Okay, now we are on YouTube now.
Okay, so hello everybody. Here is Xin Bian speaking. I'm from Zhejiang University, Hangzhou, China. It's my honor to be the host today. Today we have a speaker named Matej Praproponik. So Matej is the head of the laboratory for molecular modeling at the National Institute of Chemistry and professor of physics at the Faculty of Mathematics and Physics, University of Ljubljana. He studied physics and received a bachelor degree and PhD from the same university. Afterwards, he carried out postdoc research in the theory group at the Max Planck Institute for Polymer Research in Mainz, I think where he works with Kurt, right? Kramer. And then he has also held several visiting positions, including the Computational Science and Engineering Lab, where he is located in ETH Zurich. That's why make us a colleague also. And later he was visiting Institute for Mathematics and its Application in University of Minnesota, and also the Cavalli Institute of Theoretical Physics, which is in Santa Barbara, and also the Cavalli Institute for Theoretical Physics in China. I think it's in Beijing, right? Matej is also a former chair of the PRAISE, which is a partnership for advanced computing in Europe. So it's a big committee steering the scientific computing. He served as a president of the Slovenia Biophysical Society from 2015 to 2019. He serves as a council member for the CFSM and as scientific council member of the National Institute of Chemistry. He is a recipient of the ERC Advanced Grant in 2019 by the European Research Council. I think this is very challenging, very difficult to get the Advanced Grant. It's very competitive. His research is focused on computer simulation of soft and biological matter. The focus is on developing and combining innovative computational and theoretical methods with further augmented by machine learning techniques. So the purpose is to study the complex molecular systems. Matej is my good friend and also collaborator. And today we are very honored. So the stage is yours. Please go ahead.
Thank you very much, Xin. So I'm also very happy for this invitation, and I'm also very glad to be able to present our work. Let me, sorry, this one, slideshow. So do you see my slides?
No, not yet.
I already shared the screen. So perhaps I should share the screen, or you should.
You have two screens or one?
Okay. This one and
Jen has the.
So you see my slide?
No, Matej, you are the okay.
No, it's fine. No, it's fine. Now it comes.
Sorry. Okay, now you see my slides.
Yes. Go ahead, please.
Okay. Thank you very much. So today's talk is going to be about multiscale simulation of open molecular systems. And first we have to define what open systems are, right? And from the thermodynamic point of view, we have three big groups of systems. So one are isolated systems. These are systems with no exchange of matter and energy with the surroundings. And the typical thermodynamic ensemble is then a microcanonical one, which is the most normal ensemble to be simulated with molecular dynamic simulations. Then we are having closed systems, which actually exchange energy and with the surroundings, but they don't exchange matter. So this means that they have a constant number of particles, which then, of course, corresponds to the canonical ensembles at constant temperature. And then we also distinguish open systems, which actually exchange both matter and energy with the surroundings. And this actually then leads to a fluctuating number of particles and fluctuating mass. And this actually corresponds then to ground canonical ensembles in equilibrium. And this will be actually the topic of today's talk, these kind of systems. Of course, I said multiscale simulations. So first I will introduce what multiscale simulations are, and I will introduce the method that we actually developed to deal with such multiscale simulations. Here I will focus on concurrent multiscale simulation. That means that the system is described on different level of resolution simultaneously at the same time in the simulation box, and different domains of the box are then treated with different level of detail. And actually, I will introduce how you couple this kind of different level of detail within one simulation. And then I will also present our coupling between atomistic models of soft matter and molecular liquids with the supramolecular ones, which is actually that this means that one coarse grain bit represents many molecules, not just one, for example. And then I will end up with this on the methodological point of level with an open boundary molecular dynamics, which is our approach how to simulate, how to open up the box, simulation box, and simulate molecular liquids with molecular, so using molecular dynamic simulation with open boundaries, so replacing the standard periodic boundaries with open boundaries, which can then allow for general, so for fluctuating number of particles, and simulating liquids in ground canonical, or in general soft matter in ground canonical ensemble with molecular dynamics, which is not standard way how to use simulation of molecular dynamics, which is basically typically used within the NVT or NVE ensembles using periodic boundary conditions. I will then show, I will employ this methodological, all these methodological methods I will showcase their applicability on biomolecular applications, in particular DNA molecule in salt solution, and then also this liquid crystalline phases of DNA which we encounter in viruses or in the nuclei of the cells. And I will end up with the open boundary MD of a DNA molecule. And just at the end, I will show how this methodology can be used in ultrasound propagation through liquid water. So multiscale modeling and simulation. So this is actually the typical sketch how to present what this means. Actually, on y-axis we have a length, spatial scale, and then on the x-axis we have time. And actually, multiscale means in our case concurrent multiscale approach, where we couple different levels of resolution within the same simulation box. So here in this picture we see atomistic protein, okay, depicted here with the secondary tertiary structure cartoon representation, but this is actually an atomistic protein, and then embedded into the this multiscale solvent. So in the first few solvation shell we have a atomistic representation of water, whereas for farther away, where basically the solvent plays the role of a reservoir, we can represent solvent or water here in this case with lower resolution, so lower level resolutions with coarse grain models. So either this balls, these blue balls, they represent one molecule, or in this case 4 molecules, because here we use actually Martini force fields where one bit represents 4 water molecules. And then now the idea is that these water molecules, they of course move around as freely as they do, and when they go, depending on their position, so the distance from the center of mass of the protein, they actually adjust their resolution. So if they are close to the protein, they are represented atomistically, while when they move further away, they just change the resolution to the lower coarse grain resolution. And then if they go back closer to the protein, they will also get back to the atomistic solution. So you can, go even further on in this with this coarse graining, and you go beyond the particle-based description of the liquid, and you go basically you start using the computational fluid dynamics description, where this can be actually simulated using Navier-Stokes equation. So the dynamics of the liquid is governed by the Navier-Stokes equations, and actually this part can be then numerically treated either with finite volumes or finite element schemes from engineering, whatever you like, or Lattice-Boltzmann from physics, if you prefer that. And if you go even further on, you get to the nanofluidics. So basically, of course, higher up you go with the length scale and cheaper method to use. This actually allows you to get to longer time scales and length scales, but actually you lose some details. So basically, the idea of the multiscale is that you actually preserve the details in the part of the box where this is necessary, where you don't have to have such a high level or computationally expensive methods. You just resort to a lower resolution, and this actually implies also to cheaper, computationally cheaper methods. But in this way, you don't actually lose any detail. You just gain, you get the best of both worlds, and you gain the computational efficiency. So actually, today's talk is about molecular dynamics simulation. And actually, so we are, if you come from bio world, so biomolecular simulation are typically simulated using atomistic simulation, and ND is a very powerful technique because actually it provides all the atomistic details of this kind of systems. Or you get actually access both to structural and dynamics information, and also then this actually then also relates to the function of these biomolecules. But the problem of atomistic simulation is, of course, that because of you have a lot of, you are treating a lot of particles and degrees of freedom in these kind of systems, you cannot actually often reach large length and long time scales. So they are difficult to capture typically, but or you have to actually resort to powerful computers. So the other idea is that then you start coarse graining. So this means that you start using lower resolution models. And basically, this allows you, if you go from here to that, to cover a much larger portion of length and time scales. So in this phase diagram, although now the price to pay is actually the atomistic details are usually lost. And the multiscale simulation is actually, the idea is that you couple both of these two descriptions. Like in this case, you use just these high resolution models only around the macromolecules where you really need this kind of detail, while further away you can use much lower resolution models. And the idea is just to use simulation as a magnifying glass, and you zoom in or zoom out into interesting part of the system, and there actually treat system on the appropriate level of detail. So how we do that in molecular dynamics? So we develop this adaptive resolution scheme address, and actually here is just for the simplicity. You have a simulation box of methane-like molecules here represented with these 4 red spheres. And the coarse grained representation of such a molecules, you can use just one spherical molecule. Now this molecule has, of course, vibrational, rotational, and translation degrees of freedom, whereas the coarse grained representation only has translation degrees of freedom. So now the problem is, I mean, in all this method, the problem is how to go from a coarse grained level, so the cheaper level, to the more expensive high resolution level. So on this, so from the high resolution to coarse grained, it's not a problem because usually, typically, just average some information out. Well, here you have to actually introduce back the missing information. So our idea was to couple this in MD simulation using this linear ansatz of forces. So we are coupling atomistic forces, which are acting between the atomistic molecules, with the coarse grain forces, which is basically can be derived from coarse grain intermolecular coarse grain potential of this coarse grain representation of this system. And this can be done on several ways, how to get to the coarse grain interaction. So you can either go via structural coarse graining. Basically, if you want to reproduce the structure of the molecular liquid, then you can actually derive these coarse grain interactions via the structure-based coarse graining, and you can reproduce the, for example, radial distribution functions of the atomistic ones, the corresponding atomistic system, or you can do other top-down approaches or neural network. Nowadays, potentials doesn't matter. The idea is then that you do introduce this coupling via this smooth coupling weighting function, which is like an order parameter. And this weighting function is depicted here with this blue and red line. And you actually, the value 0 corresponds to the coarse grain part of the system, and the 1 to the atomistic part of the system. And then you have a smooth transition in order to facilitate this reintroduction of the atomistic details from coarse grain to when the molecule moves from coarse grain to the atomistic part of the system, and that you give the molecule enough time to equilibrate and find the proper orientation by itself on this journey. And actually now, of course, in general, so this is the idea is that this is the same liquid everywhere. It's just represented here with the lower level of model, and here with the higher one. So basically, usually if you just couple two different molecular models, they will not have the same chemical potential. And what will happen is that the molecules will go into the region with the lower chemical potential, and you will get a non-uniform density profile, which is not what you want because the liquid is the same everywhere. And to actually compensate this difference in the chemical potential between the different representation of the liquid, we have also this thermodynamic force, which basically corresponds to the negative the derivative of the chemical potential density between the two parts of the system. And actually, this allows you to couple in the end very different models. They don't have to be so basically, they don't have to have the same chemical potential. They don't have to have the same structure. You are free what you couple actually. So basically, you can also couple the two different atomistic models of water, for example, SPC and TIP3P, if you like. And you are rather flexible in what you couple. But actually, these schemes that allows you to get this concurrent coupling of different resolutions, level of resolution within one simulation box during the course of MD simulation. What is important here is also that this force coupling scheme actually obeys the Newton's third law, which is important for conservation of linear momentum. And actually, this is also important that if you want to couple everything to the Navier-Stokes equation or computational fluid dynamics, where actually you want to assure that the linear momentum is properly transferred to the liquid. And actually, this method actually guarantees you that this will be the case. Okay, so you can then. Why do we bother with this kind of couplings? Because actually in MD, in all these biomolecular simulations, they are all done in some, so all the biomolecules, in this case, we show DNA molecule, this blue molecule in the middle. Actually, they are all embedded, so solvated in water solvent, so in water solution or salt solution in this case. And in all this MD simulation, the treatment of the solvent is the most expensive part of the MD simulation. So if you want to get a methodological speed up for such a simulation, so it makes sense that you put your effort in how to actually speed up the treatment of the solvent. And because this will actually in turn lead to the speed up of the whole MD simulation. So what the idea here is that you can use this atomistic resolution of the solvent only around the biomolecule, in this case DNA molecules, and then further away you have this basically you represent water with just so oxygen and 2 hydrogen with just 1 bead. In this gray bead here, this is 1 water. And in this way, you actually simplify the description of water. This water also don't have an actually all the electrostatic interactions are basically included in this effective in the coarse-grained interaction, and this speeds up your simulation quite substantially. So, but you don't lose any detail because actually where all the chemistry and everything's interesting is going on, it's around the DNA molecule, and there everything is actually represented atomistically. So you get a speed up of MD simulation while retaining all the details where this is really needed. So then you can, of course, with this kind of methodology, basically you can simulate different properties, structural properties, dynamical properties. In this case, we actually computed the electric constant of DNA molecule and part of the DNA molecules. And here I'm showing you the electric values, a comparison of the electric values for different sizes of atomistic regions. So basically this number here actually denotes the radius of the atomistic region. So basically the radius from the center of mass of the DNA molecules outwards. And of course, the larger you can, with this method, then you can play around to see how large the atomistic region has to be in order to actually reproduce the reference all atom results, where you, instead of having this multiscale solvent, you just have the high resolution solvent everywhere. So in this case, because here you don't have electrostatic interaction, you can enlarge the radius of the atomistic region, and sooner or later you will get to the value where actually you reproduce the atomistic results. So what we wanted to show here is that if you enlarge this value, so this infinity actually means all atom simulations. Okay, so these are the reference values, and you can see that you can quite quickly get to the same values as in the all atom simulation. So basically, you don't have to simulate the whole simulation box using the atomistic solvent. You can just, you need this high resolution only to a certain distance away from the atomistic macromolecule. And here we also show the dielectric constant of water. And so on the x-axis, there is a distance from the DNA center of mass. Red one is actually the DNA dielectric constant, so the dielectric constant of water using the all atom simulation. And you see that, okay, it of course actually varies in the vicinity of the DNA molecule, but then farther away from the DNA molecule, it actually levels up to the bulk value of 80, approximately 80. This depends on the water model, atomistic water model that you use. But you see here that actually, and here are the different values of this multiscale solvent, no? For different values of atomistic region, a radius of the atomistic region. And you see that at the vicinity of the DNA molecule, you reproduce the dielectric behavior of the molecule, while farther away you don't get to the value of 80. Okay, you see that, but this is actually to be expected because, as I said, our coarse grain model does not have any dipoles or any electric interaction. So this is just an effective water model. And basically it does, you cannot calculate dielectric constant with it, because actually these molecules, as I said, they don't have a vibration and rotational degrees of freedom. So if you freeze up the rotation, you actually you lower the dielectric constant. So this is sorry. So basically, this behavior here is because of the fact that the coarse-grained model of water does not have any dielectric, so it does not have any electric dipoles or anything. So basically, you cannot calculate the dielectric constant farther away from the DNA. But the most important part is that here, where the dielectric constant is actually varying in the vicinity of the DNA molecules, you can reproduce the atomistic behavior of these water models. And here is actually just another measure of distance from the nearest DNA atom. We get the same result. Okay, so this was just one molecule, but what we were interested in was actually this crystalline phases, liquid crystalline phases of DNA, namely, you know, in nuclei or in viruses, your genetic material, the DNA molecule, we have our length of the DNA molecule in our body is 2 meters on average, and this has to be packed into the very compact space of a cell. And then you actually encounter these liquid crystalline phases. So DNA molecules actually, so here you see basically the DNA molecules, the neighboring DNA molecules, they get these fibers that are actually arranged into the different liquid crystalline phases. So depending on the concentration, you can go from isotropic to cholesteric to hexagonal and orthorhombic. You have different phase transition between different phases of this DNA molecules. And we actually wanted to study these phase transitions using MD simulation. So what we did is actually we simulated this 16 by 16. So all these blue circles, this is actually a DNA molecule. There are DNA molecules pointing out of the screen. So basically you have infinite fibers. This is a top-down view of such a system, so, embedded into the salt solution. And the whole system is actually put into the semi-permeable membrane, which actually allows the water and ions to pass through, whereas the DNA have to stay within this area. And actually, the idea is that in this way you can measure. So the idea how we wanted to study the phase transitions was to actually compute the osmotic pressure, which is a little bit non-standard way for MD simulation. Typically use virial expressions and compute pressure, thermodynamic pressure, not the osmotic pressure. This is a little bit, you have to actually, the way how we do it is actually we compute the interaction between the DNA molecule and the membrane using Lennard-Jones kind of a potential, where we just you have to integrate so everything's all in interaction over the surface to get the interaction between the molecule and the surface. And this is actually the way how we compute this osmotic pressure. And what you get is actually the whole point is the following. So basically, depending on the ions, the type of the ions, so the valence of the ions, the idea is, of course, if you want to pack, DNA is a very negatively charged molecule. So how you can actually make them into this very compact phases, if they are negatively charged, how do they actually condensate? It was a question. So, but this is due to the ions, and actually the ions actually then allow these molecules to condensate, because you get these kind of bridges between the molecules and on all the, and also this electrostatic screening. And the idea is that this is only you can only get this for higher. You cannot get this for the normal salt solution, sodium chloride, but you can get this if you use ions with the higher valence. So in this case, we use spermidine, which is a 3+ ions. And in this way, we actually checked this the equation of states of osmotic pressure versus concentration of the DNA molecule for two different geometries. So for the hexagonal and orthorhombic, which they change, they are quite similar, but there are a few differences in the geometry. So we wanted to study this this phase transition. So we computed the equation of state for both phases and for different type of ions in salt. And actually, with this, you see that if you use this spermidine, you lower basically this repulsion of the DNA molecules. And actually, you also we computed, as I said, for two different geometries, for hexagonal and orthorhombic. And basically, to study this phase transition, we use these positional and rotational correlations to be the indicator of what's going on. So we have here translational orientation and rotational correlations, and we actually were able to reproduce. So here you see the phase transition. Basically, we could get to the same numbers so we use here an experimental Lindemann criterion, which is this line where the correlation go beyond the rotational correlation go beyond the value of 0.1. There is the phase transition, and actually this is actually corresponds quite nicely to the experimental values. So basically, using this multi-scale approach, we were able to actually study this kind of experimental findings. So this indicates that our approach from the methodological point of view is correct. So you can also study other phase, other parameters. So, and you see that actually, so here, perhaps you see these two DNA molecules, and this is actually the other parameters that describe the solvent. And everything is normalized for different concentration of DNA. So the idea here is to see that if you increase the concentration of DNA, that this means that the DNA molecules get closer to each other, and this of course means that the solvent in between them is basically affected to a largest degree. So you can see that for the red one, you can get quite different values of these other parameters than for the lower concentrations, which is also what you should expect. So what I was presenting you here basically was we use this kind of coarse graining, so that one molecule, one water molecule is going to the one bit. So this is so-called one-to-one mapping. So one molecule is always represented with one coarse grain bit. So there is this one-to-one correspondent, but you can go even to larger degree of coarse graining. So in this case, we actually use the same atomistic DNA molecule surrounded with the atomistic water in the same basically geometry, but instead of one-to-one mapping, we had the 1-to-4 mapping, 4-to-1 mapping. This means that this coarse grain bit here represents 4 water molecules, atomistic water molecules, instead of 1. So why is this important? Because, for example, one of the most used force fields, coarse grain force fields for this biomolecular simulation is a Martini force field, which is actually a force field where the basic principle is such that one coarse grain bit represents 4 heavy atoms, carbons, oxygens, so on. In the case of water, this means 4 oxygens. This means actually 4 waters. So now you go from 4 waters to 1 coarse grain bit and vice versa. And this is actually, this allows you to go to coarse grain your system to a larger degree. So basically your coarse grain model is even cheaper and more computationally efficient. But of course you lose more details than previously. So this coupling is more difficult to actually achieve than the one-to-one. Apart from the rest, you need also algorithms. We had to devise a new algorithm, Swinger, which is basically just which actually concurrently assembles, disassembles, and reassembles water clusters on the fly. So basically, you have to have like 4 water molecules that are close to each other. You have to actually redistribute them during the simulation into among the coarse-grained beads. Because the problem is that, of course, water molecules in water has this tetrahedral structure of these hydrogen bonds between them. But these hydrogen bonds between the water molecules, the lifetime of these hydrogen bonds is on a picosecond time scale. So basically, these water molecules, they come together, they form these tetrahedral structures, but then they reassemble. So basically, for this coupling, you have to, one of these coarse-grained beads does not represent the same 4 molecules during the whole simulation. Okay, so you need to have an algorithm, which is this Swinger, that actually distributes these water molecules among these coarse-grained beads, so that you know at each time that what. So a given coarse-grained bead, that you know this information, which 4 molecules it represents at any given time during the MD simulation. So basically, in this way, you can couple this Martini and atomistic water models that I presented, or you can go even higher. You go to, for example, to the dissipative particle dynamics models or simulations, where basically you have this mesoscopic bead. It can represent arbitrary number of molecules. So basically, if you put an Avogadro number there, you will get, okay, what you lose is actually this molecular description of the liquid. So you will simulate basically Navier-Stokes simulation, but of course, you will not longer have a molecular description. But this here, to the difference of Martini, where this mapping is always 4-to-1, here you can have an arbitrary mapping, so a bead can represent any number of molecules. But if you want to actually preserve this connection to the chemistry, to the molecular description, basically it was actually shown that you cannot go to an arbitrary number of molecules for these DPT beads. It can only work for up to 30, I think, was shown that you can get this correspondence. So basically, okay, you can still, if you go 1 to 10, it's still much higher coarse graining as 1-to-1. So this is, of course, what we aim for. So in using this Swinger and Andres, we can also couple now atomistic and DPD water. And DPD is actually a nice model because it allows you to study all this non-equilibrium flow simulation using DPD is basically it's MD with a special potential, soft potential, repulsive potential, and a special type of a thermostat, but it's just a variant of MD. So basically, this coupling is a very natural. It's a natural from the methodological point of view, but it allows you then to study many different systems. So basically here is just a funny representation of this Swinger algorithm, and it's just a clustering algorithm. I will not go into now this explanation. It's just it's a very simple. You have to have you have to basically follow the molecules. You can distribute them into the lists and then actually use also some simulated annealing Monte Carlo to improve the clustering. But basically, this is very cheap. It's costs nothing, and you can do that. You don't have to do this on every time step of the MD simulation. It's enough that you do it, for example, at any Verlet list update. So every 1,000 time step. So basically, it does not add any computational cost to the MD algorithm, but it allows you then to do this coupling of atomistic models with supramolecular models of lipids. And okay, so basically, as I said, MD is a method where you solve Newton equation of motion, while DPD is just a special version of the MD, where the force is actually it has three contributions. One is this conservative force part, which is this repulsive soft potential, and then you have two additional random and dissipative parts terms, basically that represent a stochastic thermostat. So these are the thermostat terms, and actually the sum of this is DPD. So basically you can go from this description of a liquid to that, and you can switch between both of them. The important part of the DPD is that it actually a method that that basically describes the dynamics of liquids on the mesoscopic length scale, and this means that you have to show that the transport of linear momentum through liquid, which is very important for properly describe the hydrodynamics, is preserved. And what we show here is actually that our multiscale method actually basically satisfy the linear momentum conservation, and this means that the linear momentum is properly transported through the liquid. This allows you then to actually do this kind of study, for example, target drug delivery kind of model, so situations. In this case, this is something that we actually simulated with at the ETH for 10 years ago. This is quite a long time ago. So it was a buckyball and a flow of water past the buckyball. So the idea of buckyball was actually this would be like a carrier for gene or drugs, and then you put it into the blood flow, and then you can do the targeted drug delivery. So everything, well, the idea was to couple the continuum hydrodynamics with the atomistic one, because actually these nanoparticles are not, basically these are not colloids. They are smaller than colloids, and a non-slip boundary condition at the boundary of liquid and the nanoparticle does not hold. So you have a partial slip boundary condition. So you have to determine a slip length, and the idea is that you get this slip length that determines the boundary condition for the continuum solver. You get it from the MD, and that's why you have every nanoparticle is surrounded with this atomistic water around, and actually then this allows you to basically couple the continuum hydrodynamics with the particle-based description of the liquid. Now, if you forget the continuum hydrodynamics, you can also have this kind of coupling. So this is a star polymer melt. So all these colors depict actually star polymers, which are these polymers that they have a center monomer at the center, and then they have arms of linear polymers going out of that. So, and the idea is that here what we wanted to do is actually, if you focus on this part here of region of interest, we wanted to open up this system in X direction. And by opening up, I mean to allow molecules to exit or enter into this region of interest. And this in the region of interest would actually represent then the ground canonical MD simulation. Now, the problem with the ground canonical MD simulation that they are not there is not that there were not algorithms around. They were, but there were some algorithms devised in the 90s, but they were all shown on the Lennard-Jones liquid. And the idea is that if you have a ground canonical ensemble, you need your number of particles in your system fluctuates. That means that you have to delete and add the molecules into the dense liquid. Now, deleting is not a problem, it's adding. So you have to find the temporary holes in this in this liquid where you can actually insert the molecule, and this is very, very hard. So it was always done for simple systems like Lennard-Jones. But if you want to put a star polymer into the polymer melt, this is impossible. So, but here comes the idea of this adaptive resolution. Instead of inserting molecules into this atomistic region, we actually insert them into this coarse grain part. Coarse grain molecules, they have a much softer intermolecular interaction between them. and it's much easier to insert. And this soft interaction actually allows also for the overlap of the molecules, so it's much easier to insert the molecules into this coarse-grained part of the liquid. So this is just some additional regions that are not part of the system where we insert the molecules. And then when they move toward the region of interest, they increase their level of resolution. When they enter into the region of interest, they are already fully equilibrated. So that the region of interest is basically described with this high level resolution, and it actually allows for ND simulation with the fluctuating number of molecules. So this is basically the way how to actually open up the periodic boundary condition. So in X direction, we have this the system is open, while in the Y and Z direction, we still use the periodic boundary condition, but we could, in principle, open the system also in all three directions. Now, the idea is that this is then the ground canonical MD, if we are in equilibrium. But this goes even further. It actually allows you to do, so this is this open boundary molecular dynamics. So we replace the periodic boundary condition with open boundaries. And in equilibrium, this allows you to do this. So basically, the non-canonical ensemble, while you can prescribe, as a matter of fact, any boundary at the boundaries. So you do this through this external force, which is actually reflects. Basically, the whole idea is done by matching the momentum fluxes and energy fluxes on the inner and outer region, and actually you can prescribe any boundary condition on this box. So here you can put this everything under shear or under uniform flow, or what we use it actually for we use it to get to the ultrasound description on the particle level through the liquid. And then actually this allows you then to do all these kind of different general boundary conditions on your molecular system, which is what basically, while preserving all the equation of motion in this region of interest. So we don't introduce any additional terms into equation of motion on MD. So the inner part of our system actually adapts to what we are doing at the outside of the system here, where we introduce the boundary condition. So in principle, this is then also similar to all this non-equilibrium MD simulation like slot or Doyle's algorithm and so on. But there actually, you know what, you know your final stationary state of your system, and then you drive your system by changing the equation of motions towards this stationary state. Well, in our case, we don't care what the stationary state is. We just need the boundary condition, and then the system will get to the stationary state, whatever this state will be. So we are more flexible in terms of what you can actually prescribe at the boundaries than because the other one, these algorithms for non-equilibrium MD, they typically what they are used for is, for example, for Couette flow or this kind of situations where you know what your stationary state is. So, but here we can use much more. We are much more flexible in what to prescribe at the boundaries. And so you can use this kind of simulation also for, we come back to this DNA molecule. But here now the point is that actually what we do here is that we no longer use a particle coarse-grained model like either 1-bit or supramolecular models like Martini or DPD. Instead, we actually here we use the implicit water model. So there is no, basically water here is just an implicit water. So we have the explicit water only around this first hydration shells of the DNA molecule. So further away we use, as a coarse-grained model, we use implicit water model. So the idea here is then why this is important. Of course, if you have an implicit water model, then there is no water here outside. It's just the dielectric constant. So all the electrostatic is screened by the dielectric constant, but there is no explicit water, and you just have ions. Now ions, the physiological concentration of salt is 0.15. But all the simulation and also the simulation that I showed at the beginning of the lecture, typically they are conducted at 1 molar. So this is much higher concentration. And the reason why this is the case is, okay, on one part, there are experiments also performed, some experiments are also performed at 1 molar concentration, but the real reason is actually that because the physiological concentration of 0.15 means that if you want to get to any reasonable statistic for these ions, you need to have a large system containing a lot of water molecules in order to get to the acceptable statistic for ions. So if you want to have a high number of ions in order to get some statistics for ions, then this will imply that you need to have even many more molecules, water molecules included in the box to get to the 0.15 molar. And basically, as I said, the solvent is the most expensive part of the MD simulation. This would be extremely computationally expensive for larger systems. So in this case, using the implicit water, we don't have water, no? So basically we just have ions, and this is cheap. So we can go to the physiological concentrations while retaining while retaining the computational costs, because basically we have explicit water only here around the DNA molecules. Now, of course, why this is open boundary? Because here we actually have to now, from the point of view, if you look at this explicit water part, this part is actually exchanging water molecules with the surroundings. So just around the DNA molecules, this part will not have the constant number of water molecules, so they will fluctuate. And that's why this is open boundary. And basically, okay, from the side, the system looks like that. So we have an explicit part of your simulation with DNA molecules and all the salt solution represented on the explicit with the explicit water model and ions. Then you have this buffer region, which is also basically overlaps with this hybrid region of address. And then you have a part of the system where you have ions in a dielectric medium with epsilon, but with no explicit water molecules. So the coarse grain part of the water is basically the implicit water. And that means that then this allows you to actually simulate all this biomolecular system at the physiological conditions with the same, so with not some outrageous computational cost that you would have if you wanted to have basically an explicit water everywhere. And why this is important? So we here have, I'm showing you the compensation charge, and you see that basically, as I said, typically in order to actually facilitate the problem, so to overcome the problem of this low concentration of salt, they use 1 molar salt solution instead, and this is this blue line, and you see that 0.15 molar actually it's not quite the same. So basically 0.15, this is the physiological concentration. This charge compensation is a bit different than for the 1 molar. So basically, in principle, you're not simulating the same system. Okay, and okay, so this is this charge compensation. Sorry, I was showing you previously the density. So this is basically 1 molar is the blue line, and 0.15 molar is the red line, and you see that the charge compensation is not the same in both systems. So basically, if you want to simulate this system at physiological conditions, then you should basically use 0.15 molar salt solution. But then, of course, either you make a very expensive computation, a very expensive simulation using all atom description everywhere, or you use our model, and you will get the correct description of surrounding solvent at the same costs as I mean, you will have to have a really fast simulation if you use this model. Okay, so as I said, you can describe, with this open boundary, you can prescribe any boundary condition at the boundaries of our system. So this is a DPD water now. And we introduced the ultrasound. Ultrasound is basically a sound with the frequencies higher than 20,000 hertz. So anything about that, it's ultrasound. And basically, the attenuation is actually very frequencies dependent. So you can introduce the ultrasound then as this perturbation of pressure here at the boundaries. And then we wanted to study this the propagation of ultrasound through such a DPD particle-based description. Now, the ultrasound is basically a fluctuating hydrodynamics phenomena. So it's typically modeled with the continuum methods, but not so much with the particle-based method. So this was actually one of the first attempts how to simulate ultrasound to particle-based models. We could reproduce. So basically here I show just typical plots that you get from the different, so you have different frequencies and you have also all the sounds attenuated. Yes, this is you can actually study this attenuation, how it depends on the basically on the frequency that you actually induce at the boundaries. And actually, this is basically the idea of my ERC grant. So we will use this ultrasound for ultrasound guided drug delivery. Where ultrasound is used, as I said, like in this sense, we basically you put your drugs into some carriers and then you deliver them to, for example, to the tumors, and then you you shoot these carriers with ultrasound so that they explode and they push this explosion. They push these drugs into the area where they are really needed. And basically, yeah. This is done in my USC project. And actually to conclude, so I presented, so we were talking today about open systems, where basically a number of parties, so the molecular system, they exchange energy and mass with the surrounding. And we derived the methodology to do this kind of ND simulations. This is called this OBND, which allows you to prescribe any boundary condition at the boundary of your molecular system, and then you can perturb your system in very so it's in any, I will not say any way you want, but okay, you are free to do many things. The idea here is, of course, that we solve this by actually this adaptive resolution scheme. We solve one problem that we actually encounter in this way, namely the insertion of complex molecules into a dense liquid. And as I said, it's general and allows for efficient molecular simulation of biomolecules, for example, solvated in any bathing salt solution, especially at this physiological ionic strengths. So if you couple everything to this implicit water, you will get to the so you actually coarse grain away the water, and this speed up tremendously the simulation. So here is the acknowledgement. This was done with some collaborators, of course. Stash and Yulia and Yuri were my PhD students. Yulia is now an assistant professor at TUM. Yuri is in Barcelona doing postdoc, and Stash has a app company. He is a computer scientist. Then basically, I am also collaborated with DNA with Rudolf Podgornik, who is actually now at China, in Beijing. Then this collaboration with the supramolecular solvent and using the Martini force field, we were collaborating with Stuart Maring, who is the driving force behind the Martini force field. With open boundary simulations, we were collaborating with Rafael Delgado Boscaglione from Madrid, and Petra just did this simulation with Ultrasound. And I also thank the Slovenian Research Agency for funding and you for your attention. Thank you.
Okay, thanks, Matej, for a very, very interesting and fascinating talk. If there is a question from the audience, please just unmute yourself. Okay, maybe I start with one. So I know I follow your work for many years, right, Matej? And we wrote a review paper together, or article. So to me, the most difficult part is, although your algorithm of address can theoretically accelerate a lot because you reduce a large degree of freedom in the cross-screen side. However, in reality, you know, when we write software, like all lamps, we write everything on lamps, for example, they are designed not for hybrid simulation. So they typically designed for a single scale. Either you use cross-screen or you use molecular dynamics, the full atomic scale. And therefore, if one want to blend the two scales or multi-scales together, usually we are facing the difficulty of really nice implementation to achieve the theoretical acceleration. So do you have comments on this? Like,
yeah, I do have a comment.
You see on this, you know, people, I think they struggle to use this address or other.
Yes, so this is a bottleneck of, I mean, it's not a, yeah, well, it's a bottleneck, currently a bottleneck of all these multi-scale methods. I think there is Philip Neumann in the audience.
Right, Philip is here.
Yeah, hello, Philip. He tried something to do that with his approach, how to do the efficient code about this kind of couplings that I presented today. So there is a challenge. Yeah, I agree. So I think that you are also involved in this kind of area.
Right.
Yeah. Also, yeah, I agree that this is actually, so what I presented today was a methodological part of the story. But then there is another part where you have to, so this actually, from the methodological point of view, there is no, I mean, this offers, like you said, great, it has a potential for a large speed up and everything. But then, of course, to actually get to that, you also need an efficient code. And this means basically that there is still some work to do, how to get from this, what I showed today, to something that you can use on supercomputers.
Right.
You need to have yeah, you have to understand that also all these lamps and all this stuff, ND algorithms were developed for a few decades to get to the point where we are now. And this multi-scale, you know, now all these couplings, actually you have to focus on couplings and how to describe already for couplings of this particle-based description, there is quite a big effort. But imagine now that you have to couple it, like I showed you with the hydrodynamics codes, they are completely different in architecture.
Right.
Everything. So you have to somehow get to the couplings. I think, well, you know, the same problems because you are involved in this, like me, like Philip, that there is still a lot of opportunities for every one of us, not just problems. I mean, to actually, but okay, this is another topic. So this is basically code development, how to get from to implement all these methods into a code which would allow you then really to be super efficient and
back at Brown, we with George started some initiative, but it was still very small effort, I would say. It doesn't solve all the problem, but it needs really, you know, deep understanding and really to design the infrastructure from the scratch to do this.
It's a lot of problem because you need a lot of different profiles. So you need domain scientists, and then you need also software engineers, and they have to collaborate in a coordinated way for quite a substantial amount of time. So you need to have all of this. If you have all these conditions fulfilled, and you are lucky, then you might get to an efficient package. And then actually, yeah, but it's worth it because if you get this to run on big machines, then you can study large complex systems which are important for all this biomedical and this kind of simulation. So ideally, then you will have a machine. Your doctor will have a machine in her office, and they will make your personal medicine with it and everything.
So we'll just wait for Philip Neumann to do that, right? Philip.
Well, I mean, there are a lot of efforts, but I know that Philip is working on that as well. Yes.
Yes, I know. He has many projects.
I just saw him here, so that's why I mentioned. Yeah.
I know. I was chatting with him privately down there. Sure. Yeah. So
basically, at my university, at least, we currently build up another big computer that will just at least heat up our rooms, which is already good. So it's the first step in the right direction. And I see that there's much work for the HPC guys around here. That's also great to see. Mate, hi, long time no see. I would also have a question. Indeed, this time not on the HPC aspect so much, but indeed on the methodology. So when I look through the adaptive resolution schemes and the reviews on that and all the methodologies there, I also stumbled over the point of n-body potentials, right? So typically you have those two-body potentials like Lennard-Jones, and then you basically know what to do and how to coarse grain things, how to put things together. Do you have any idea how one could do this methodologically if you have more than two bodies involved in collisions?
So you're asking if you have, instead of this effective interaction here, which are two bodies, you have some neural network potentials or something like that? Which are now popular. Yeah. But I would,
something like that, or if you really have like in interaction of particles, not only like two bodies interacting with each other, but really like three at a time, right? So not like Lennard-Jones where you have two sides interacting, but three or four.
You cannot use this scheme because this is for two-body interactions, right? So you have to invent something else, I would say. So far, I wanted to omit this because there was still many things to do here on this level. But yes, this could be a very welcoming, because this can be then used for, if you have these coarse grain forces here, if you use some neural network potential, then this might be then the way to go. No? But
I see. Okay, because I was wondering. Thanks. I was wondering whether you could do something like, you already did the clustering of particles, right? Whether one could go somewhat in this direction and just trick a little bit.
Yeah, so what we did actually similar here with this supramolecular coupling, basically. Here you have these kind of things, but here is just basically we still use two-body potential. All this clustering actually is just numbering. It's basically in the lists, not really in the interactions. So the interactions are still two-body, and actually this also this is also a limiting factor in some way, that you cannot go in the DPD so you cannot use, you cannot go to the supramolecular coupling. It cannot go to a large degree higher up. So you cannot, for example, use cluster of 100 molecules, because I don't know how you would really, this would be, anyhow, we are lucky because this was shown by George, I think George group, Piuk and Igor, I think, if I was not mistaken, show that they can reproduce the DPD properties up to the level of 30 molecules. So we are lucky somewhere that this approach cannot go anyhow, even if you don't want to do this hybrid things, you cannot go with this story too high up. But also for this happening, I don't think that you can grow really, we can go to 10 something. But actually, from the point of MD, this is already substantial, because you have this is already offers you a big speed up. It's just that it's difficult to go to higher couplings, and it might be that then you would have to use what you just proposed. But this would complicate this would complicate your life even more. Oh, yeah. Okay. Yeah.
I'm sure it does. Thanks a lot, Matej.
Well, you know, the point is that you always want to solve all the problems where they are still easy, and then slowly you go beyond that. But sometimes it shows that it's not that difficult, because this is how when we actually derived this swinger, I also thought that this was going to be quite difficult to achieve. But in principle, to go from 1-to-1 to this supramolecular coupling is, at the end, from the on the methodological encoding point of view, it's very, very simple. So it's nothing difficult. Of course, not to go to 100, but let's say 10. But sometimes, perhaps sometimes some stuff really looks difficult, but then when you start working on it, sometimes it shows up. It's not that difficult. But okay, here I don't know. This is still an open question what you ask. Yeah. So we didn't work in that direction.
Matej, I have another question. I want to know your opinion. You know, nowadays there's a very strong trend that people do coarse graining using neural network, right? There is a potential called deep potential, for example.
Yes. So this is actually, this is what I said, that these are many body potentials. Yeah.
Right. And then in view of this machine learning trend, so people already did coarse grain. Are you aware of any work on hybrid method using neural network, or you think is it possible to have both the level of
I think that there was some work in China. Actually, this was an ex-postdoc of Luigi, and it was Han. He is working, Han, I think.
This Han from Beijing, right? He was also working with Wei-Nan Yi.
But I'm not sure that they really did the hybrid. Yeah.
But I think if I remember, they were doing deep potential. They coarse grain quantum to classical and classical to coarse grain. It was not hybrid, I think, isn't it?
It was not hybrid. No, that's true. But the problem is that I'm not so sure that you need really hybrid there. So it also depends. You know, something is that you want to do it, that you show that it can be done. But then you have to also think of a real system where you would need this kind of coupling.
Right.
Because here, somehow, this, you know, with this thermodynamic force, we are allowed to couple atomistic, and these coarse grain models, they don't have to be really fine-tuned to the atomistic model.
Right. But because your thermodynamic force is adaptive itself, right?
Yes. So I guess that this, so far, where there might be also some work to be done is actually how to derive this thermodynamic force, which is now done in a quite engineering way. So there is this iterative procedure, but I guess it can be done in a more rigorous way. So on a theoretical level, it is rigorous. It's just the way how you numerically arrive to this to the expression. It's still, I would say that it would require some more development, I would say. It's still engineering. But actually, this is the point. So why we didn't go into that, because if you want to really go, I mean, sometimes you'll just, you know, you do some fine tuning and then you go with some third ingredient that it's not that fine tuned. You spoil the whole thing. So you would really need to think of a system where you would need this kind of a coupling.
I see. Any more questions from the audience?
So I have two questions about the coupling algorithm. So Matej, I'm thinking if you do this kind of concurrent coupling, actually the time step of the simulation actually is bounded by the atomistic level. So actually, if after you do the coarse graining part does not need that small time step. So do you have any thinking? So
this can be further optimized. So far, we are using the time step of the atomistic system, no? But yes, coarse grain part actually allows for much larger time steps, and basically you could think of any this multi-step, not just multi-scale methods. You would have to also have multi-step methods somehow you could employ here. So the speed up here in our case really comes not from the time steps, larger time steps. It comes because your atomistic part, it's much smaller than in comparison to the full box. And this allows you to actually, this is where the speed up comes from. But yeah, I mean, there are still some areas where you could improve the methodology. As you said, this would then actually go on the level of integrators, I would say, MD. You have all these forces, you have these different, it's like this RESPA and all these kind of methods that were actually derived in the 90s by Mike Tuckerman and co-authors. Actually, I was also, my PhD was devoted to this kind of methodology, so I'm aware of this kind of what. So I guess that there is room for improvement. Yes, I agree.
Yeah. So I understand that if because this is three-dimensional, if you just do coarse graining of the outer side, actually you reduce the degree freedom significantly. But if you can also get some speed up in the time domain, maybe you have twofold acceleration for.
Yeah, so then you get even, so they are still, as I said, there is still room to improvement, and you can get the twofold, yeah, as I said. And then the third one, to put everything into efficient code and have a supercomputer, and then you are flying. No?
Yeah, another question is about the boundary, the coarse graining boundary. So how close you can move the boundary to the atomistic region? Is there any theory to give us?
Okay, so one thing is this the width of this hybrid boundary between the regions. This should be such that this part does not see this one. So this is like an effective radius of this interaction. This is one thing, but the other thing is, of course, that how large is this? Basically, how far does the hydrogen bonding affects the properties? Because coarse grain molecules, they don't have hydrogen bonds inside. So you can basically here, there are theories where they did where they do study this effect of hydrogen bonds, but using the same level of resolution. It depends on this theory description, but if you, this is actually allows you here really by hand study that, because you don't have hydrogen bonds in the coarse grain liquid. This will actually, and then if you compare it to the all atom results, you can exactly see how far you have to go in order that this effect disappears. So this is basically really a numerical tool to study the distance of this theory. So the effect of hydrogen bonds. So here by hand you can do this stuff. But basically one rule is also that you should not put, you should have a radius big enough that this hybrid region gets into the bulk of the. So basically, I know you have a macromolecules, this perturbs the surrounding solvent, no? And but to a certain distance away from the macromolecules, you reach the bulk properties of the solvent, as you would not have a macromolecules. And now the point is that this hybrid region going from coarse grain to atomistic should be placed into that area somewhere where you are already in the bulk. It should not be close to the macromolecules. So this is also one condition. Basically, but this correlation holds that happen because basically solvent molecules, they don't have they cannot approach the macromolecule too closely. Basically, should not be a correlation follow of the macromolecule, this hybrid region, in other words. So I think.
Okay. Thank you.
Oh, hi, Mate. This is Zhao Yan. So I'm very interesting talk. I'm quite interested in this adaptive like resolution scheme. And so I have a question about your hybrid region. So when we down to the like maybe nano or mesoscale, so the motion is kind of control everything. So here I'm wondering, so when you validate your maybe hybrid like this kind of adaptive like a scheme, so do you test the mechanical like a wave propagation? Like you send a kind of mechanical wave from either like atomistic region or your coarse-grained region and see how the hybrid region can somehow affect the propagation. So that's my question.
So hybrid, thank you very much for this question. So hybrid region is an artificial, this where the artifacts are, because this is not here all the, so the idea of this hybrid region is that you don't want to perturb. So basically, okay. The condition when this hybrid scheme works is a bit different than a condition of coarse graining. So if you have an atomistic, you take the atomistic system, you always take the atomistic system or higher resolution system as your reference. And then you do the coarse graining, okay? And the condition for coarse graining is that you get everything, you reproduce the atomistic level on a level of these central masses or effective interaction sites. So if you reproduce the RDFs of the central mass as computed also from the all atom simulation, you are satisfied if you want to do the structure, for example. But this is not the condition for this hybrid multiscale method. So in this, the condition for the hybrid level is that in the all atom part of your hybrid simulation, all the properties have to be exactly the same as in the reference all atom in that part. So this is a different condition. So here is the condition that all atom, so this is just a buffer. The coarse grain part is a buffer. So basically you want to have that atomistic, all the properties of atomistic subdomain are the same as you would simulate everything atomistically and focus on the same region. So this is a different as for coarse graining. Now the hybrid, as you said, this is not, because this is ansatz, this is an ansatz. This is what you want is actually to have a scheme that you have this, you need this hybrid region so that, as I said, that when these coarse grain molecules come here, they have to reintroduce this missing orientation and everything. So you should not overlap with any surroundings. So they have to find the proper space and everything. So you need to allow them to do that. Because actually we orient them actually randomly here at this boundary. And if you would just have turned on the interaction between all atom degrees, which are not, because the weighting function is 0 at this boundary, and then you slowly turn on the atomistic interactions. So basically you would have an overlap with other molecules, and this would cause explosions in your algorithm, right? But since you slowly turn it on, actually these molecules, they found their right orientation. So this is the purpose of hybrid region. But the idea of all this is that basically with this mixture of these forces, of course, this is not proper physics. So you have artifacts, and basically the idea is that you screw up the atomistic part as little as possible. So that's your idea. You cannot derive it from any theory. So you will not get there is no such thing as a perfect coupling.
Okay.
So
I got
yeah, no, and now with all these tricks that I show you, we actually were correcting all these artifacts that they come out of this hybrid region. But the idea is that, yeah, that your all atom part is as little perturbed by these artifacts that you cause with these different couplings. Because all these hybrid methods, okay, we have this hybrid region here and this kind of a coupling for address, but you have many other methods that will couple similar stuff, or for example, in continuum and particle description and everything, they all will have artifacts because there are no such things as perfect couplings. The only thing what you want to have is that the couplings really, they cause as little problems to your system as possible. So And if you manage to do that, then you're done. Yeah.
Yeah, thank you very much for the further explanation. I now have a better understanding about your scheme. So very nice.
Thank you.
Thank you.
Is there any more questions? And if not, we thank Mate again, okay? Thanks, Mate, for this excellent talk. We keep in touch, okay?
Sure.
Thank you. Thank you.
Thank you very much for the invitation.
Have a good afternoon. Okay.
Yes, have a good night. You are very late,
Yes.
I guess.
Thanks a lot.
Bye-bye, Philip. Yes.
Okay.
Bye then.
Thanks. Bye.